Okay. So then, welcome everyone to another meeting of the seminar for graduate students in probability. The goal of this seminar is that the researchers can give a talk in a rather simple way so the students can understand. And the idea is that after this, they can work in a thesis or start a PhD project or something else. So today it is my pleasure to present Wei Shu, and he did his PhD in China in the Beijing Normal University. And after that, he's doing a postdoc at Humboldt University of Berlin. So thank you very much for giving that.
Okay, thank you. Today I want to introduce some work, my work about the Renai theorem for spectrally positive stable processes. Actually, we know that Renai theorem is the first studied, established to understand the distribution of local time of Brown motion, and they are established by Ray and Knight. Okay, almost at the same time. All right. Here is I first introduce why I studied as my motivation. Okay, about from the local time of Brown motion and from continuous state branching processes, and also from stochastic volatility dynamics. And then we introduce the main result. First about the Renai theorem. Then we say something about the characteristic function of the local time of stable processes. And we also provide some equivalent representation for the local time. And we finally give a short proof for our main theorem. And finally, we give our conjecture about more general Levy processes, okay? So I first introduce our motivation. The first motivation comes from the local time of Brown motion. We assume B to be a standard Brown motion, okay? LBXT be the Brownian local time, okay? That means the local time of the Brown motion. And tau BL, zeta is a positive constant, means the first time that the amount of local time at 0 first existed zeta. Okay, it is defined like this. This is the first time the local time at the location at level 0 exceeds zeta. Okay, and the Renai theorem taught us that these processes, we change this x to t, okay, as time t, okay, as t go to for t positive, this processes actually is a branching diffusion, okay, and also it is a solution, the unique solution to this SDE. This SDE means this is the initial state, and this is the whole continuity diffusion, okay? And we can also write this SDE into this form. In here, the WB will be the standard Gaussian white noise. We know that this is a critical continuous state branching process here, okay? That means the Brownian local time can be connected to the critical continuous state branching processes. So what our question is about, for other general Levy processes CASI, what is LCASI? Okay, what is this processes? This is our first motivation. Our second motivation comes from continuous state branching processes. As we know that for the discrete state branching process, it's well known as the Goldwasser processes, okay, GW processes. Goldwasser process is actually the Markov chain. It is used to describe the evolution dynamic of the population, in which the individual dies or produce offsprings independently at the integer point time. It usually defines as this, okay? This summation means the offsprings produced by the individual in the last generation, okay? Because NR is a RID, integer, positive integer valued random variables, okay? They are independent. That's because each individual will produce their offspring independently. So because this is Markov chain, and with the help of the Martingale theorem and the Markov processes theory, Markov model theory, we can study the Gottwalson processes very easily. And actually, a bundle of beautiful properties of Gottwalson processes has been studied and established. Okay, and especially there's scaling limit. That means as the Gottwalson processes, there the branch rate is close to zero, close to 1. That means the mean of the offspring is close to 1. And the scaling limit has been established, completely established by Quattro, Watanabe, and also Lee. And it always can be written into the solution of this SDE, okay? And in this SDE, this term is drifting, the drift term means the growth, this B is the growth rate, okay? Growth rate. And this is the diffusion term. Diffusion term can be understood as the binary branching. And this is the jump. Jump means there will be a individual will produce a cluster of offspring. That means a lot of offspring, not two, not finite. It means a cluster of the offsprings. Okay. Zeta means the eta t means the immigration. So every solution for this SDE will be a continuous state branching processes. Okay. And also any continuous state branching processes can always be an unique, strong solution to SDE in this form. Okay, so that means for the scaling limit of Gottwalson processes has been well established completely. Okay, so but for the general branching processes, it means it is a continuous time but discrete stochastic population model, and its branching mechanism is age dependent. Okay, that means it is not homogeneous. It is always dependent on its age and also on the characteristic of each individual. It is first introduced to study the complex biological population. Okay, and its population size ZT always can be written into this form. That means X, this capital I means the collection of all the individual in the population. And for each individual, its sigma X will be its birth date, okay, or birth time. And Lx means its life length. So ZT means at time t, how many individuals are alive at time t. So this will be the summation of this guy. Okay, t is less than its birth time, but smaller than the birth time plus its life length. That means it's still alive at time t. All right. General branching processes, GB process, okay, usually is not Markov processes and also not a Martingale, which makes the study of the general branching processes very difficult because the modern probability theory usually cannot be used here. Okay, so, but if the reproduction processes is used to describe each individual, the individual give birth to their offspring, offsprings. Okay, if this process is short memory, that means each individual will give birth to its offsprings in a very short time. Then so that the rescued general branching processes will converge weakly to the standard continuous state branching processes. Okay, especially it will, without jump, it will be a branching diffusion. Okay, you can find it in this paper. So our question is, if the reproduction processes have long memories, or it's a heavy tilt, okay, what will happen? So what is the scaling limit of the general branching processes? So this is our second motivation. Our third motivation comes from the stochastic volatility dynamics. This is our main motivations. Okay, in 2017 and 18, we have Fries and Gasserill and Jason and Woodenbaum. These 5 people, and they studied the volatility, okay, in over the stock market. They find that the log volatility behaves like a fraction bond motion with host exponent it almost equal to 0.1, which means that the volatility is very, very rough, okay, very, very rough. So here is the figure from their paper. They consider the difference of log volatility, okay, with step size delta. Okay, as delta go to 0, you will see that it is always like decrease like this power law. And with the index Q, that Q is almost linear to Q, okay, like this. And you see actually the rate is about 0.1. So that means the host exponent is 0.1. That means the volatility graph is figure is very, very rough, okay? So they introduced 3 very, very famous rough volatility model. The first one is a fractional Burgondy model. You can find it in this paper, okay? It is defined in this way. This capital E means the exponential martingale of these processes, okay? These processes, as h smaller than 0.5, you will see that actually this is can be considered as a fraction bound motion. Actually, this is a fraction bound motion, but not standard, just how to say, alternative fraction bound motion, okay? And the second one is a fractional OU processes, also can be found in the same paper. It is defined in this way, okay? It is the exponential of VT. VT is an OU process, but driven by a fractional bound motion. Fractional bound with h smaller than 0.5. The third one we call fractional Hessian model. Oh, sorry, this is in wrong paper, okay? It is established in Jason and Woodenbaum, 2006, okay? Not this paper, another paper, okay? The model is defined in this way. You see that this one is a T minus S. This is a dominant is a T minus S alpha. Alpha is from 0 to 0.5. Okay, you see as S close to T, that means this one will go to infinity. Okay, so that means the process will fluctuate very fast, very, very dramatically. Okay, so that's why makes the simple path very, very rough. So we call this 3 model rough stochastic volatility model. All right, another thing is you see this figure. Okay, this figure tells shows the volatility around 2000 in 2008, September 12th, okay, to November 20th, and the origin point actually indicated the jump or the sub-raise more than 2.5%. Okay, more than that means a big raise. Okay, a big raise. And Battis and Duffy, Pan, and Eric, they prove that actually there are a lot of sub-raise in the volatility. This means the volatility will be raised very quickly in a short time. We call this one as a sub-raise. Moreover, Sahalia and Battis they also prove so that the sub-raise enjoy clustering property and also the self-exciting properties. What it means? It means clustering means you see that the sub-rays always get together. This phenomenon, we call it a clustering. Okay, another thing is self-exciting. Self-exciting means that this sub-rays will lead to some new sub-rays. Okay, that means there always some interaction between the sub-rays. Okay, so and otherwise, this figure we plot the volatility from 1999 to 2019. You will see that the volatility actually, when it grew up, jump up, it will always decrease, come back. That means volatility have mean reversing happening in the volatility. That means the volatility will tend to move to the average level. That means that it will always come back, okay? Will not far away from the average level. Moreover, they also show that the volatility has a long memory. It means that the correlation between sigma t, this is the volatility, okay, and sigma t plus capital T, this one will decrease at some power law as t, capital T go to infinity. So this means there's correlation after a long time still very strong. So now we compare the some very well-known stochastic volatility model about the fractional OU processes with index H, okay, and also fractional Burgundy model with H, okay, Heston model and a fractional Heston model, and also the affine processes with jump, okay. First, we for their continuity, okay, because except this guy, other models is driven by fractional bound motion or bound motion. So the model, the process is always continuous, except the last one, because there is jump. Another one is a mean reversing. Mean reversing for the fractional OU model, okay, this is always mean reversing, but for the fractional Burgundy model, that doesn't work. It is always fluctuate, it will not come back. And Heston model and the fractional Heston model is has a mean reversing, okay, but and also a fine jumping, a fine model, and also this one can be considered as a continuous state branching process with increasing, okay. All right. Now, certainly we consider there's a roughness for the fraction model with H smaller than 0.5. They are always rough, okay? Even for the fractional Heston model, they are rough. But when H large or equal to 0.5, they are not rough. That means it's how the continuity is large or equal to 0.5. Okay, if it's large or equal to 0.5, we will see this process is not rough because every diffusion model driven by Brown motion, it is always hold the continuity with the index large almost equal to 0.5. Okay, so they are not rough compared to diffusion model. Is it rough or not? Okay, the fourth one is a subrace. In all this model, okay, continuous model, there's no subrace. And in the affine model with jump, there is a subrace. The subrace is coming from the jump, okay, coming from jump, not coming from the diffusion, coming from the jump. And self-exciting also excitation, okay. For the first one, OU model is driven by Brown motion. It's just a plus of Brown motion, okay. There's no self-exciting. Heston model actually is it is a CB processes, okay, a CBR processes with a continuous state branching process with a migration. Individual will give birth to new offspring, so this is why they have self-exciting. And also affine processes, these three models have self-exciting property. And a long memory, when H is larger than 0.5, that means it will be fractional Brown motion with index larger than 0.5. We know that fractional Brown motion, this kind of fractional Brown motion have long memory, okay? So all the model driven by fractional Brown motion with H larger than 0.5, they will have long memory, okay? But for other model, they will not have long memory, even for the affine processes which jump, okay? If the B is positive, that means the mean reversing happens, then long memory will not happen, okay? You can check it, even with in random environment, it still doesn't work. So our third question is, can we construct a stochastic volatility model to involve all the factors? Okay, all the things in one model. So this is our third motivation. Why they are connected to the local time of the stable processes? Because from the beginning, we have shown that the local time of branch motion is a continuous state branching processes. It's a Hessian model and also a special affine processes without jump. They have the self-exciting, and also they have some they have some mean reversing. Okay, so that means if for the stable processes, we know that the jump will be more higher, okay, more large. So this will make us to think about maybe the local time of the stable processes will have long memory and also have self-exciting, because local time processes of branch motion will connect to some branching processes, and we also maybe consider conjecture that the local time of stable processes will also connect to some branching processes. Okay, so that's why the self-exciting property maybe also existed in the local time processes of stable processes. Okay, and subrace is obvious because the branching because of stable processes, the jump is a heavy tilt. Okay, it's a jump, very heavy. So that's why we consider the local time of the stable processes. All right, in order to give our main result, I need to introduce some notation. First, we denote Z C as the spectrally positive stable processes with Laplace exponent like this, okay, B lambda plus C lambda to the power 1 plus alpha. Okay, it also can be written into this form. And here we just consider the B is positive or equal to 0, not negative, okay? C is positive. If it is equal to 0, it will be degenerate, okay? Alpha is from 0 to 1. If it is equal to 1, it will be a branch motion. So we are not interested in this form. So when B is equal to 0, that means there's no drift. No drift means the stable process is transient, okay? When B is positive, this means the stable processes will drift to the negative infinity, okay? Will drift to the negative infinity. All right, we also denote W, this capital W, as the scale function over zeta. It is defined standard, okay? When it is equal to 0 on the negative half real line, and positive on the positive half real line is determined by this Laplace transform, okay? This is a very standard, okay? All right, we are also interested in, we are also need to use the derivative of the scale function, W prime, okay? Notice that W prime will go to infinity around 0, okay? Will go to infinity around 0. So it is a singular at 0. All right, and also denote the L C xt be the local time of C. It is joint continuous two-parameter processes and satisfies the well-known occupation density formula. Okay, is defined like this. There are many ways to define the local time. Here we just we use this one because it's much easier to be understand for every non-negative measurable function on R. So because Eisenbaum and Caspi in 1993, they proved that if the original processes is not continuous, then its local time will not Markov. So that means the stable processes, for the stable processes, its local time will not Markoving. Okay, will not Markov. So this will make our study about the local time very difficult. So we still define the stopping time torque CL zeta be the first time of the amount of local time at level 0 exceeds zeta. Okay, it defined as before, just for the stable processes. So we are interested in the local time stopped stop at this stopping time. Okay, this Lx. Okay, our main theorem tells that for any zeta positive condition on this stopping time be finite, we have this local time. This local time actually is a unique weak solution to this stochastical Valtteri equation. Okay, Valtteri equation, because different to the standard Ito integral. This one, in the integrand, there will be a t. Okay, from 0 to t, they also have a t here. All right, so that means this is not martingale or semi-martingale. All right, here in alpha will be a composited partial random measure with intensity ds mu alpha dy dz. Mu alpha is the Levin measure over the stable processes. Okay, this is the Levin measure. Okay, from this equation you can see that actually the local time is contributed by the jump over the stable processes. Each jump will contribute to the local time in this way through its scale function wt minus s minus wt minus y. So from 0 time from 0 to minus t minus s belongs 0 to y in this interval, you will see that this one is increasing. Okay, after y, it will decreasing. Okay, that means its contribution over the jump at the beginning will increase and decrease after the time interval and after the jump. Okay, from here it's increase and then decrease. Okay, here the first term actually is the mean contribution. Okay, the mean over the local time. When b is positive, we see that bw actually will increase to 1. So that means this one will decrease to 0, this term. So the mean will decrease to 0. Okay. Secondly, this stochastical integral can be understood as the Ito integral. That's because the difference of the scale function satisfies the following two upper bound. Okay, this makes this stochastic integral can be defined as an Ito integral. Thirdly, because this is local time, okay, it is stopped at the torque CL zeta. Okay, stopped here. So the height of the local time, the height of the stable processes actually is finite. So that means the local time will be fall into 0 in finite time. So that means x zeta t will equal to 0 in finite time, and after this stopping time, it always stay at 0. Okay, it will always stay at 0. So that means 0 actually is a trap for these processes. Okay. All right, this is our first main result. This result actually give a stochastic, give a representation for the local time in the form of stochastic increasing. All right, when b is equal to 0, we have said that the stable processes is recurrent. So the local time at level 0 will go to infinity as t go to infinity. Okay, so we have that this local time, this stopping time is always finite. Okay, but when b is positive, the process is transient. The local time at 0 will be finite almost surely. This will make this stopping time will be finite. Okay, always finite. That means this process is actually the subordinator queued at an independent exponential time with mean here, okay? It has a Laplace transform this, okay? So in the next theorem, we saw that when B is positive, we stop the stable processes at the last time he arrive at 0, okay? We stop at this. Then we consider it's a local time. We found that this processes actually is a unique weak solution to the stochastic Bartoli equation with the initial state zeta be an exponential random variable with mean U00, okay? And it is also independent to the partial random measure in alpha. That means this one will be a randomness, okay? Will be exponential distributed random variable. Okay. This is our second result. With the help of the SDE, we will see that we can prove that x zeta actually the local time process is actually the local time, okay? It is locally hold continuous, okay? With over any order smaller than alpha over 2, okay? When alpha is equal to 1, will be Brown-Mosen. It will be smaller than 0.5, okay? So, and the second one is actually for any theta in this interview, we prove that the Holder coefficient, okay, defined in this way. This is the Holder coefficient theta here, okay? This coefficient has finite moment over all orders, any order, okay? This one has been proved by Foreman in 2018, but we can reprove it with the help of the SDE very easily, okay? Okay, so with the help of the stochastic Bartoli equation, we can study the characteristic functional over the local time. Firstly, we define a function kt, capital KT, okay? It is a power function defined like this, okay? And also we define an operator. It is acting on a c-valued function f in this way, okay? It is very familiar. It is very similar to the characteristic of stable processes actually. For example, you replace this one as a z y and it's a zy. It will be the Laplace transform, Laplace exponent of the stable processes, okay? But here it's different. So, and C minus is the space of all complex number with non-positive real part, okay? And B, R plus C minus is the space of all bounded C minus valued functions on R plus. This is all, these two are standard notation, okay? We also denote F star G as the convolution of these two functions. It defined like this. This is also standard notation. Okay. Here, this is our third main result. For any lambda in the C minus and G in B, okay, this function, we find that it's a its characteristic function, a characteristic functional have this form, okay? The exponent here is a K star V lambda G, okay? This convolution. V lambda G is a unique global solution to the nonlinear Bartoli equation. Actually, they have the same, they can also, this equation also can be considered as the Riccardi, nonlinear Bartoli-Riccardi equation, actually, all right? And this form is not so convenient to understand. We will give some other representation. It will be much easier to be understand, okay? Here you need to notice that this W prime is the derivative of a scale function is singular at 0. So V lambda G at 0 should be considered as the right limit of K star V lambda G at 0. Okay, we saw that actually this one, this convolution is will convert to 1. So this makes this V lambda G will be continuous at 0. So that means this one, as capital T go to 0, it will convert to K star V lambda G 0. This is continuous. All right. As we have said, this representation is a little complicated to understand. So we provide some equivalent representation. All right. The first one is we saw that actually x zeta t is a solution to this equation. So it is very close to the continuous state branching process now. Now we come back to the continuous state of the standard continuous state branching processes. It is defined as a solution to this SDE. Okay, this is a drift. This is a diffusion. This is a jump. Okay. Okay. In this term, U3B is a drift. Okay. You can understand this one as a jump. Okay, but a different jump, different type of jump, because this one is still continuous, but it's a summation. It's a summation of finite, countable guys. Okay, this one. So when alpha is equal to 1, you will see that this one it will be equal to 0. Okay. Oh no. This term will equal to 1. Okay. This one is also equal to 1. So you will see that actually this one will turn to be the continuous state branching diffusion. Okay, this will be the branching diffusion without this term. When alpha is equal to 1, this guy will reduce to this term actually. All right. So now we can see that actually the local time over stable processes is branching processes, but general continuous state branching processes in any form. You can see from here, you can see it is very similar to the standard continuous state branching process. What's the difference? The difference is here. Okay, T minus S alpha to the power alpha minus 1. Alpha is smaller than 1. So this is very rough. All right, now give the equivalent representation for the characteristic functional. Okay, we define some Riemann-Liouville fractional integral and derivative operator. Okay, this is a standard notation with a here. A is equal to 0. When a is equal to when a equal to 1, it will be the standard Riemann-Liouville fractional operator. Okay, so now the characteristic functional, okay, the V lambda G is the unique solution to this fractional Riccardi equation. This is a generalized fractional Riccardi equation, okay, in this form. So this is B, the drift, okay. This is when G is equal to 0 will be the Fourier transform, okay, characteristic function. And V lambda is the operator. Okay, compared to the Laplace transform of the Laplace transform of the continuous state branching processes. Okay, you will see that Vt is the solution to this generalized Riccardi equation. They are very similar. Okay, B minus B here without G, okay, will be this operator, remember V alpha. V alpha is very close to this form, okay. So from these two theorem tells us that the local time processes of a stable process actually is some kind of a continuous state branching processes, not standard. It's more generalized. It's more general, okay. All right. Now we give the outline of our proof for the main result, the main theorem. Okay. We first notice that for the stable processes, C, we can approximate it by a sequence of rescaled compound portion processes. Okay, K zeta n, it will convert to C. And this compound portion is heavy tilt. Have heavy tilt, okay? The jump size is heavy tilt. Actually, the Pareto disputed. And the Lambert and Smarto, they prove that the local time of Kc0 Kc0n will converge to the local time of Kc. So that means we just need to make out what is the limit. What is the limit of the local time of Kc0n? So in order to characterize the limit, we recall a very important result from Lambert. Okay, Lambert shows that the local time of compound portion processes actually is equal in distribution to some special CMJ processes. Okay, Crump model Jacques processes, CMJ process. It's defined by the following three properties. The first one is the life length of the ancestor is distributed as the set bias distribution over lambda. Okay, why? Because at time 0, we know the particle at time 0 or individuals at time 0 still alive. Still alive. That means his life length is a conditional distribution. Okay, from the from the statistic, you will see that actually the distribution will be the set bias distribution. Okay. The second one is the offspring over each. The offspring will have the common life length distribution lambda, capital lambda. Capital lambda is the Pareto distribution. Okay. And also each individual will give birth to their offspring to their children following a portion processes. We rate gamma n. What is gamma n? Gamma n is here. This is gamma n, okay? The jump rate of the compound portion. It will satisfy this condition, convert to the B, the constant B, okay? The drift. Okay. And in our previous work, we have shown that the CMJ processes actually can be described as marked Hawkes processes on 0 to infinity times R plus with the intensity gamma n, okay, the arrival rate, Zn S minus, this is the rate, and lambda dy is the distribution of the mark, okay. So the population processes ZNT can be written into this form. This is the ancestor. It is alive at time t or not. This one tells us this. This guy tells us if there's a guy born at time s, it is still alive at time t or not. This is its life length. If its life length is larger than its age, it means it's still alive. If it's smaller than this guy, this means it has been died. So t minus s is the age of the particle or the individual. This is why it is life length. So this makes sense. Okay, it's easy to understand from this equation. All right. So what do we need to do? We just need to consider the scalar limit of this ZNT. All right. From previous, we have seen that we define some function. Okay. The first one is RHNT. Is the relevant of this function. Okay. It's defined as a relevant equation. Okay. Also define RNTY. It is a 2-parameter function. It defines with the help of the RHN. And from our previous work, we have shown that ZNT, actually, this equation, okay, can be written into this form. The difference is here, okay. In this one, it is a compound portion processes, okay. This is this is a portion random measure, okay. This is a portion random measure. And in this, you will say that this is a composited portion random measure. That means I have moved the mean away, okay? Move the mean out. So actually, in some sense, you can understand this one as some martingale, actually. You can understand that as a martingale. but different to martingale, but you can understand it as martingale. So in the previous, we have shown that the local time of C0n will convert to the local time of the stable processes, okay? So what mean we just need to consider what's the limit of this guy, xn, okay? Rescaled, this is the rescaled processes, okay? Rescaled. It will convert to the stable process, the local time of stable processes. So we just need to make out what is the limit. So in order to study the limit, you see that we first need to make out what is the limit of RH and what is the limit of this function. Okay. Firstly, we saw that the rescaled resolvent, the integral of the rescaled resolvent will convert to the scale function. This is very important. Okay. With the help of this convergence, we saw that this first two terms, that means the contribution of the ancestor to the population, actually can be approximated by this term, okay? By this term. And we also saw that the second function, the two-parameter function Rn, actually the rescaled, its rescaled over this function will converge to Wt minus y. So the will convert to the difference over the scale function. So with this help, we will see that actually this stochastic integral actually can be approximated by this one. Replace this guy by this, okay? So put these two together. Oh, okay, still. Don't forget that this composited portion random method, sorry, this one, its intensity is this guy, okay? We saw that this one will converge to this guy. And hence, the composited portion random method will converge to this composited portion random method, okay? This is another one. So put them together, come back, we will see that these two guys will convert to this one. This one will convert to the stochastic integral with respect to the new portion random method. So we get what we want. So this is the proof. All right. Now give some conjecture about the local time process over more general Levy processes, okay? We assume Cauchy as a spectrally positive Levy processes. It's determined by its Laplace exponent in this way, okay? Defined in this way. Here we still assume B is a negative, okay? And the Levy method satisfies this. That means it has finite mean, okay? The mean is finite. All right. For its scale function W, actually the absolute continuous on the half real line, okay? And its derivative we still denote as W prime. And L Cauchy tau x is a joint continuous almost surely, if only if this integral is finite, okay? This integral is finite. You can find this one in the book of Breton, okay? This is a well-known result, actually. So now we under this condition, that means the local time is jointly continuous. We conjecture that the local time process is this one, okay? Defined as before. It is a unique weak solution to this stochastic laboratory equation, okay? Different to the stable processes, it is here. The difference is here. We have an additional term. It is driven by Gaussian white noise with intensity ds dz. So this one is W prime, not W. Okay, this is the derivative of the scale function. This is the drift of the Levy processes. This is the diffusion coefficient of the Levy processes. And this is the jump of the Levy processes. Okay, so now you can see that you can see the contribution for each term over the Leavitt processes. How do they make contribution to the local time? Okay. Here, you will see that actually, if we let the jump size get smaller and smaller and smaller, actually you will see that this one actually can be approximated by its double prime times y. Okay, actually that means when the jump size gets smaller and gets smaller, then you will see that this term will be vanish. Okay, will vanish. Okay. So actually, this result has been proved. I have proved, and it is in preparation. This equation is right actually. What I didn't prove is about the pathwise uniqueness for this equation, different to the standard SDE. Okay, because different to the standard SDE, because of the impact of this T, the uniqueness, pathwise uniqueness will be very, very difficult actually, will be very, very difficult. And for the standard SDE, the uniqueness has been, had been proved in a paper of Lee and Dawson. But for this one, the pathwise uniqueness is still an open problem, even without this term, just driving by Brown motion or driving by Gaussian white noise, the pathwise uniqueness is still an open problem. Okay, that's because this is a Hodel continuous. If it's this one, it's a Lipschitz continuous. Everything is well done. Everything is very easy, and the uniqueness, pathwise uniqueness, strong uniqueness has been proved. But for the Hodel continuous, no, still problem, still open. Okay, still unknown. All right, that's all the thing I want to introduce. Thank you.
Thank you very much.